In this lesson, we're going to talk about gamma ray bursts, the biggest bangs in the universe, since the big one. And like so many other parts of these courses, this is something that no one saw coming. People didn't predict this ahead of time. It was a complete surprise when these things were discovered, and they're pretty amazing things. They were discovered as a byproduct of the Cold War. During the Cold War, in the 1960s, there was a test ban treaty which said that different countries, USSR and USA, were not allowed to test atom bombs. Now, if someone tried to test an atom bomb underground, that was something you could spot because it would generate earthquakes and seismometers could pick it up. But could people be testing these things in the atmosphere? Both sides were worried that the other side might be illicitly testing bombs in the atmosphere. So the Americans decided to build some satellites to make sure the Russians weren't illicitly testing nuclear bombs in the atmosphere.
So these satellites were launched in the 60s mainly. They were called the Vela satellites. And you can see two of them here. They actually launched two at a time, and they would come apart. So there's a top and a bottom here. This is on the top of a rocket that's going to be launched. And the idea is that these things had what we called scintillators, big pieces of sodium iodine crystals that could go through and detect gamma rays. Now, nuclear explosions, it turns out when they go off in the atmosphere or in space, produce a very characteristic pulse. A pulse of gamma rays that fade away, and then another set of gamma rays that sort of leak out over a few seconds. And so they're pretty sure what to look for. So in 1967, the year I was born, there was a surprise. And that surprise happened, the first one, on the 2nd of July, 1967. And the detector saw a burst of gamma rays.
Oh no! The Russians were testing bombs in the atmosphere!
But fortunately, World War III did not ensue because we understood the physics well enough, and they realized immediately that the radiation was unlike that expected from a nuclear explosion. And so it was sort of filed away. Now, it turns out that these things ended up being very common. But let's remind ourselves about gamma rays before we proceed further.
Okay, so here's the electromagnetic spectrum. Starting at very long wavelengths of meters up to kilometers, which we call radio waves, down to centimeters, which are microwaves, infrared at 5-10 microns, visible light at half a micrometer, then ultraviolet X-rays, and the very shortest are the gamma rays, with wavelengths less than the radius of an atom. And because their wavelength is very short, that means their energy is very high, so these things pack an enormous punch.
Yeah, we tend to measure their energy in, for example, MeV, in mega electron volts. And so if you remember that the rest mass of an electron is a half of an MeV, 511 keV, these things, these gamma rays, have more energy in them than the rest mass of an electron. So they really do, they're big photons. Now, gamma rays are not things that are easily made. And because they are so have so much energy, they're not that easy to make.
Yes, so one way would normally we can produce things by heating something up. If you've got temperature of a few Kelvin, you're getting radio waves out. Temperatures like that of the surface of the sun, you have order 6,000 K produce visible light, but you're needing tens to hundreds of millions of degrees and up to produce gamma rays.
Right, so that's hotter than even the center of the sun.
Yes, of course, the center of the sun, the radiation wouldn't get out from there. So we're talking temperatures pretty much hotter than anything that had been observed in the universe at that point. So that's one reason for thinking you wouldn't expect to get gamma rays from space.
Right, but there are other ways to make gamma rays. So, for example, if you have a radioactive, like uranium or something, when it radioactively decays, gamma rays are produced in that process. But it's kind of hard to imagine how you would suddenly make something that was just full of highly radioactive, short half-life stuffs that would give you a flash of gamma rays.
And I suppose you could also do it by accelerating charged particles. Whenever you take a charged particle and accelerate it, it produces electromagnetic radiation. But to make gamma rays, you have to accelerate it pretty damn hard. So we'll probably be talking about taking charged particles like electrons or protons or positrons or something and getting up to 99.999% of the speed of light and then send them very close to another charge, like a nucleus, so they swerve around. And that might produce gamma rays if you can do enough of it.
Right, so these are extraordinarily challenging to make, but they obviously exist, and so necessity is the mother of invention. And one of the things that they were able to figure it out pretty soon on, because they kept on seeing these events, and so
Not more Russian tests, no.
what could be doing this? They need to understand it. And the first clue came from when they had multiple satellites in orbit, and they were able to go out and see these bursts, not from one detector, but from three detectors spread out around the Earth. And so let's look, by looking at the time those gamma rays arrive, how we could figure out that these objects were coming not from the Earth, but from space. All right. Imagine we have a bunch of space stations orbiting Earth, and these things are able to go through and tell a time when a gamma ray burst reaches them. So how do we tell where that object is based on their time of arrival? Well, because light travels a speed over time, you can imagine that depending on where the object is, it'll arrive at a different time. So if it, for example, is on planet Earth, then as the light goes out, depending on how far away the stations are, it will arrive at different times. In the configuration I've done here, the arrival time in this situation is about the same each time. So we'll call this situation 1. Put up a little thing, we measure time, and we have the 3 different stations. And in this case, they suddenly get a signal at pretty much all the same time at the 3 different stations. So that is this situation. Now imagine instead the gamma ray burst is out here. What do we see then? Well, the light from the gamma ray burst is coming this way, and it reaches station 2 first, stations 3 and 1 at about the same time later. Meaning in this situation, we were to look at the 3 times. You're going to have 2 first, and 3, and 1 later. Imagine another situation where we're down here. And so in this case, the light comes, it reaches 3 first, 2 second, and 1 third. So we get a similar situation where if we plot the time of arrival at each of the stations, in this case it's 3 first, 2 second, station 1 third. Indeed, no matter where in the sky it arrives from, there is a pattern of arrival times, 1, 2, and 3, depending on the direction. And so in that way, no matter where a gamma ray burst comes, you can tell its direction. And what they discovered, of course, is that the arrival times indicated that the gamma ray bursts were coming from away from the Earth, not towards it.